This video is for lesson 2.11 homework. So what we're doing over the next 3 lessons, we've been writing those linear equations from real world data. Now we're going to look at how accurate they really are. And there's 3 different methods to determine if that linear equation is accurate. So the method we're going to use today is actually our first vocab word. We're going to use percent error. So it says, what is the name of the measure of how much a predicted value deviates from the actual value? All right, and then number 2, what is the name of a common constant finite difference? That is a common difference. So once again, all this data is real world data. I went and pulled the census records. Okay? What this is, what it says, the table shows the population of San Antonio, Texas for each decade between 1850 and 1910, determined using average rates of change. The function P of X equals 15,521X plus 3,488 could model the population data where X is the decade since 1850 and P of X is the population of San Antonio. Use the table below to answer questions 3 through 6. All right. So this is the actual data here. This is the population in San Antonio each decade. This equation was used using average rates of change, which means this minus this over 6 minus 0. That's the last thing we left off with. What we want to do is we want to use that equation to see what the values would be using the equation. Again, this is real world. This is actual. This is a predicted value. So to do that, in your calculator, start up a new graph, new blue graph, and then we're going to put that equation in there. 15,521 X plus 3488. And then we're going to do Control T. The only problem with this is it likes to round stuff off. So you do have to be careful. I'll let you know if it's not going to work. You type this equation in. So what we're going to do, we're going to go to where X is 0. And then the Y value, that is the predicted value using the linear model. I'll have to look at it in a second, babe. All right, I'm going to go down to where X is 1. The predicted, it should, according to our model, the population should be 19,009 people. So again, 8,000 was the actual, but using the model, the linear equation we made, it should be 19,000. That is a big difference. All right, so at 2, so that's in 1870, using our model, there should be 34,530 people in San Antonio. And you just keep going down and filling your table in. 50,051. 19,009. All right, 4 is 65,572. And then 81,093. And then 96,614. Okay. So what do you notice about our predicted values? Do you notice anything? They're what? Most of them are way high. What else do you notice though? The end and the start should be the same because those are the data points you used to make the equation. So those 2 data points should be included. So it's a good way to check. Do my first and last data points, are they identical? All right, percent error. So your notes from this would have been like 2 nights ago. All right, percent error, it's hard to see, is right here. Predicted value minus actual value over actual value times 100. Okay? So what that looks like, I take P of X, I subtract the actual value, and I divide by the actual value. Well, in this case, since all the numbers are the same, I'm going to get a 0. If the numbers are identical, your percent error is 0. So using better points here, predicted value minus the actual value, it is. And then what we do is we multiply that by 100. You have to put that in the calculator for every single one. That's what I mean by tedious. And I would, on the bottom of your fraction, I'd put a decimal point and then do times 100, because that should automatically switch it to decimal form. If you don't put that decimal after the number on the bottom, it gives you a stupid fraction. So what I did was when I typed it in, I put a decimal point there. Well, so we're going to round this off to the nearest whole number. 131. 131% error. Is that good to have 131% error? No, that sucks. But you have to do this for every column. So again, that's what I mean by tedious. So, okay. Because you want to know how accurate the linear model is. So looking back at the graph, I should be able to use this graph. Let me zoom out a little bit. Stop it. Menu 4.
Wait, so it's the P minus the population.
Anyways, Kenny, I should be able to use this data to say, you know, in what can we predict the population to be in 2030, 2040? And so you want to know how accurate that model is, because can I actually use it to predict what the population is going to be in 2030? That's why you want to know that accuracy. Okay, so for this one, Braden, what was your question?
No, go ahead. Just so I answer my question.
Okay, so we take P of X, the predicted 34,530, subtract the actual, and you get one number off and it screws this thing up big time. Over the actual, put a decimal point, get out of the fraction, right arrow key, and then multiply it by 100. We're rounding to the nearest whole, so this one would be 182.
So which one is the real and which one is the predicted?
Population, that's the actual. That's the real.
Well, we're dividing by the.
No, we're dividing by, I'll put the formula up there, okay? All right, so the next one. It is tedious. Welcome to real world data. All right, so the next one. 144%. Decade 4. $74%. Because I'm a math major and a 7 looks a lot like a 1. So you cross it.
So we're like, it's gonna go up and all the way back down to 0.
Maybe. It honestly depends on how accurate that line is. It really depends. It does go back down to 0. Yes, exactly. And it's just a good way to check. So what is that, 52%? And then if the numbers are the same, it's 0%. Okay, let me zoom out because the next question. All right, it says, what is the average percent error of the table? That means you have to take all of these values, add them up, divide by how many there are. So we would do 0 plus 131 plus 182 plus 144 plus 74 plus 52 plus 0. Divide it by 7, put that decimal point, otherwise it's going to give you a wonky fraction. So the average error is 83%. Should you have 83% error? No, because that means your accuracy is only 17%. That's not good. So it says, is P of X a reasonable linear model? No. Now, does it overestimate or does it underestimate? Over. All these predictions are too big. So be able to tell me, does it overestimate or if it underestimates?
Should I just put it's over?
Yeah, as long as you know, again, as long as you can tell me which way it goes, you're good.
We got the next one.
You've got the next one. Hey, here's my advice on the next one, on the percent errors. Well, hang on. We're going to do this first column together, okay? Actually, we're going to do the first two columns, make it even easier on you. We're going to do the first two columns together. We're going to take this equation, and I want to show you what it does in the graph, because there's another way you're going to have to do this. So 18, 520, x plus 148, 7840. All right, if you look at this table, you see how you get these e's in there? You can't do anything with those e's. So you cannot do this one on the graph. You have to do this one on the calculator side. So you take your equation, and for the x, you just plug that value in. Plus 1487840. Okay? Every time. But I'm going to show you a quick way. So 1487840. So now what I can do, I can hit the up arrow key twice, highlight it in blue, and hit enter. Then I just go over here to the 1. Now watch what mine does when I do this so you don't freak out when it does it to you. I delete the 0 and I push the 1. Sometimes when you do that, it doesn't type the 2 in there. It puts like another symbol in there. Don't freak out. Hit enter and your number will appear. But that's all you have to do. It's not a whole lot to type in. 06360. All right, if numbers are the same, 0%. So percent error here, 1506360. That is a lot of keys to get exactly right. It's really, really easy to mess up here. 1511150 over 1511150. Put a decimal point times 100. All right, these percentages are going to be extremely small. So I want you to round to 2 numbers after the decimal place. So negative 0.32%. That's a good percent error. Okay? So 2 numbers after the decimal on your percent errors here. Okay? What I would do all of these first. Let me check this row, because if these numbers are off, then these numbers are going to be off. Okay? Do it, let me check, and then go do your percent errors. Do y'all want the formula, the percent error formula. All right. So percent error is predicted minus actual divided by actual times 100. Hang on.